Now let's look at some examples for inferences with two populations. The mean age of a random sample of 25 people who were playing the slot machines is 48.7 years, and the standard deviation is 6.8 years. The mean age of a random sample of 35 people who were playing roulette is 55.3, with a standard deviation of 3.2 years. Can it be concluded at a significance level alpha of 0.05 that the mean age of those playing the slot machines is less than those playing roulette? When we're determining which test to use, we need to look for some key words. So far, we've learned about hypothesis tests with means and hypothesis tests with proportions. And that will carry on into Chapter 9 as well. One big keyword in this problem is mean. And another keyword is sample. So we have a mean age for a random sample playing slot machines. Notice we have a mean age for people playing slot machines, and we have a mean age for people playing roulette. And so this is how I know I have two different populations. I have sample statistics for slot machines, and I have sample statistics for roulette. And then the question, can it be concluded that the mean age, there's that word again, mean, is less than another group? Okay. So now labeling our information, we're going to call the slot machines population 1, and we'll call roulette population 2. Just writing down some information that we have. For the slots, I have an average mean, 48.7, and a standard deviation, 6.8, and n is 25. So gathering all of these numbers, 25 people, 48.7, 6.8. I can do the same thing for the roulette, 35 people, there's my n, mean is 55.3, standard deviation 3.2. I'm going to keep these values in the same order though. These are 2's, second population, and 2 is 35. I also know alpha is 0.05, so I'll need that in the Excel template when we move there, or Google. Either one is fine. But I need to set up my hypotheses, and I also need to check some requirements. So some requirements that we have, we're dealing with means. Assume normality for the exercise. So our null hypothesis would be something about the two means being equal. And our alternative, it says in the last sentence, the age of those playing slot machines, that's population 1, is less than those playing roulette. So we want mu1 to be less than mu2. You have control over which population is population 1 and population 2. You have that control. So make sure that you stay aware of that control when you go to write your hypotheses so that you ensure that your symbols are going in the right direction. Since this is what we're asking, we're going to let that be our claim, the alternative. Now I'm going to pull up my template of two mean hypothesis test with sigma unknown. I'm going to look at the independent test. And this one's set up a little bit differently in that if there was a difference between the two means, we could also consider that in here. Our class usually does not cover that concept. Our two population hypothesis tests are always, are the two means or proportions equal, or are they somehow different? We usually don't have a value in there. So this first slot, hypothesized mean difference, leave that at 0. Don't ever move that. Level of significance, we had a 0.05 level of significance, and our alternative hypothesis was less than, mu1 is less than mu2. Equal variances, we're not going to assume our population variances are equal. If our population variances are assumed to be equal, there's a different formula that's used, or the standard error changes in the denominator. So we're just always going to assume not equal variances. Again, something else you don't have to change. And now we can put in our sample statistics. So sample 1 mean, our slots are the mean, 48.7. standard deviation 6.8. Sample size for sample 1, 25. And because that n is less than 30, we assume normality. And then we move to sample 2. The sample 2 mean 55.3. Sample 2 standard deviation 3.2. N2 sample 35 for the sample size. And then notice that these values that we entered are immediately copied down here. And that's because this template allows some flexibility in whether you enter the actual data, which we don't have in this case, or you enter the sample statistics. And so that's why this repetition happens here. It's deciding whether to get it from the yellow boxes where we entered it or to actually calculate it from the data if we were to have data. And we'll see a problem like that later. And then if we come down, we've got a difference in the sample means. We don't need to worry about this estimated pooled standard deviation. This is if we switch this to a yes. Watch what happens. It changes. See, we get a value there. But remember, we're always going to say no. So that should always stay at NA. We've got our critical value, critical T value, negative 1.695. They give us some lower rejection region limits, but we really want to come down to this value right here. This is our test statistic, negative 4.509, and then we have our p-value. Notice the conclusion is to reject the null. Now before I just take that as it is, let's draw a picture and see where it fits in. So we'll draw our t distribution. I'm going to be switching back a couple of different times because I don't have these values directly in front of me. So we have the critical value, negative 1.695, and it's actually 1.696 since it's 5.5, so we'd round up to 6. And then we have our test statistic here. T-score of difference of sample means this is our test statistic. Go ahead and rename that negative 4.509. And if we're labeling this graph, we would label this side as the rejection region and the right side as the non-rejection region. And since our critical value is falling in that rejection region, we would reject the null. So that's using the traditional method with our test statistic and our critical value. If we look at the p-value, p-value was 4.35 e to the negative 5, which means 4.3, I need to go 1, 2, 3, 4, 5 and put a decimal place. So I'll have 4 zeros in front of that 4. And I always like my leading 0 so you can really see that decimal point. This is incredibly small. If we compare it to our alpha of 0.05, 2 decimal places on the alpha, 2 decimal places on the p-value is much, much smaller. 5 is bigger than 0. And so again, because the p-value is smaller, we would end up with this same conclusion of rejecting the null. The p-value is the probability that we would get these samples with these means if the population means were actually equal to each other. Since that probability is incredibly small, the likelihood that we get these samples from populations with equal means is very small. And that's why we reject the null. It must be the case that these means are different, specifically with our hypothesis test, that our slot machine players have a lower mean than our roulette players. Generally speaking, we would say our slot machine players tend to be younger than our roulette players. Writing all this up in a conclusion, because we rejected our null and our claim is the alternative, we have evidence to support that claim. We are rejecting the null, so we have evidence to support. And so we would say this as there is evidence to support the claim that the mean age of slot machine players is less than those playing roulette.